So, now in this section we are going to look at with the simple harmonic oscillator assumption, we were able to understand that the Schrodinger equation shows different energy levels. So, what happens, these energy levels show different kinds of vibrational modes for a particular system. And again, simple harmonic motion is an harmonic oscillator is extremely simplified version. Even if you look at hydrogen atom, it's not a harmonic oscillator, it's an harmonicity which is represented by the potential energy function itself. But if you look at the allowed energy states as you go down at the bottom and as you go further up, there are different vibrational frequencies are allowed. So, that is an important factor that we need to understand here and see what those vibrations are going to be. So, if you look at an harmonic potential and in a potential well, then you will see lower frequencies at the bottom. So, let me very quickly draw that to you, so that you understand that. And so, I will go to document camera for a minute, and let us see our document camera. Let us go here. So, in this case I am just going to look at the vibrational frequencies that go together. So, you now understand that whole phenomena that we have this is potential well, and let us say this is the 0 level and this is negative E. So, if you are at the bottom of it at low temperature, this is the low temperature, and as we move forward this is high temperature, and I am looking at parabolic potential energy function represented by here. So, the particle is here, they have one frequency here at a low temperature. As you go further up, then you are seeing couple of frequencies, and as you move forward you will see that lot of more frequencies are available, and the particle is getting more and more kinetic energy. Plus potential energy is also increasing as the kinetic energy is going. So, the particle which was oscillating around here now is oscillating and have few frequencies. So, if you go to this level, you may see that there are a lot of these normal modes are allowed. These are allowed frequencies, which we looked at from our previous equation, that E n was is equal to n plus minus half, etc. So, n, and then you are looking at the let us say the h nu, which is the frequency of photon. So, if you look at these are this number n is equal to 0, 1, 2, 3, 4 are called selection rule, and that shows you what kind of energy levels are possible due to this harmonic oscillator. But as you know, we said everything is anharmonic, including what we said is the potential energy function for Lennard-Jones. So, if you look at this is a potential energy, it goes like that. So, if you look at this is the anharmonic, this if you look at if it was harmonic, it will be perfect parabola, harmonic, like a pendulum. Look at the pendulum, it's moving around, that is a harmonic motion. But in this case, as you see, this is getting, as you move up and these levels, this has become anharmonic. So, you now have to deal with more components that are within the vibrational frequency that go from harmonic to anharmonic. So, now let us go back and look at our understanding of the vibrational spectra from that perspective. And again, I am oversimplifying here, but I will take you through one case study based on my own research done way back in 94, when we are looking at the problem of velocity autocorrelation, and possibly is one of the early papers where the velocity autocorrelation was converted into vibrational spectra. So, we looked at the thermal induced fragmentation of the ice, and this was understanding the vibrations in the ice, cubic ice. So, we created the cubic ice structure using a simple point charge potential function, which I will describe later, but right now I am just focusing on the use of velocity autocorrelation function in order to look at the vibrational spectra. So, if you look at velocity autocorrelation function, as you see on the slide, provides you necessary information on atomic motion with respect to time, which is very clear to us. If you take a Fourier transform of the velocity autocorrelation function, that provides you power spectra of the atom, which is generalized vibrational spectrum. So, what happens in Fourier transform, that you are going from time domain, where, as you know, in molecular dynamics you are looking at the trajectory with the time domain. And if you look at the distribution of the velocities and its correlation, velocity autocorrelation from v0 to vt, now you can see that they have certain correlation in the time domain. But if I convert that into frequency domain, then I look at the power spectra. What that means is that where is the vibrational amplitude, or and the power, that means the amplitude of the vibration, where are they confined in the frequency domain. So, if you start frequency from 0 wave number to 3000 wave numbers, which we are looking at the visible region, then you can see where are these vibrational amplitudes are confined. So, you can look at the lattice vibration, you can look at the bending vibration, librational, then you can also look at the stretching vibration that we talked about, what we call the bonded material. So, what it says is the density of states is weighted by the square of the vibrational amplitude, and those are the density of the states that we look at that atom can be in, or electrons can be in. So, if you look at the velocity autocorrelation in time domain is converted into frequency domain by Fourier transform, and that gives you a generalized vibrational spectrum, where what we mean by generalized is that the density of state is weighted by the square of the vibrational amplitude. So, now if you look at, we start again with the autocorrelation function that we talked earlier. So, if you look at on your slide, time correlation function of velocity of atoms can be defined as ensemble average. So, here is the ensemble over time as well as the number of atoms. So, we are looking at all the atoms. So, if you look at that leads to the limit of velocity autocorrelation function. So, we are looking at from 0 to tau, any time tau going infinite, then you can see that this gets this is the long time correlation function, or long time tail correlation. And if you then use that to convert that into the frequency domain using cos omega t dt, which is the Fourier transform, now you got into the frequency domain. Now, if you look at, this is the generalized vibrational spectra of ice at 210 degrees Kelvin. As you know, the melting temperature of ice is 273 degrees Kelvin. So, we are close, not close to the melting temperature. So, we are in a solid state. So, what you look at here, there are 4 peaks. One is way down here between 0 to 50, which is what we call lattice vibration. So, now you are looking at the lattice, and they are moving like a spring. So, let us look at all the atoms connected with the spring, and they are moving together, that is lattice vibration. Then you look at this one, which is torsional, and what we call is lots of vibration which are happening here, which are rotational and torsional. That is the movement of atoms around their central axis. You can look at those frequencies. Then you look at here, which is the bending frequency. This is where between H, O, H we are moving and bending together. And then we go into last one, which is what we call as the stretching frequency between OH. So, these are the spring vibration between the 2 springs connected with the oxygen atom. So, oxygen atom consider connected by 2 springs, and at the end of each spring there are 2 hydrogen atoms, one H1 and this is another H2. They are stretching. So, this is what we call, one is bending, another one is stretching. Stretching vibrations are all, as you can see, is much higher. So, you start with the low vibration of the lattice, then you look at the torsion within that lattice, then you look at the bending of the lattice, and then you finally get into what is called stretching vibrations. So, if you now increase the temperature of this harmonic oscillator model, let us say with the generalized spectra, then now you see with the increase in temperature, this particular peak has become much blunt. So, because the frequency now higher temperature, higher distribution of frequency. You can also see that Boltzmann distribution idea. And then if you look at here again, higher distribution of frequencies, torsional, bending is almost gone and become one with the torsional. And if you look at, there is increase in the amplitude of the OH stretching frequency. You now go further up, and now this we are cutting very close when there is the melting. Now you can see immediately that the lattice vibrations are gone, and if you look at here, there is separation of torsional and the bending, and here is very well defined stretching vibration. And if you look at these peaks and its location, and this is the table that we created for all these different temperature and the peak positions, what we found is that there was a very good correlation or very good match with the experimental numbers and the trends of the change in the frequency of vibration as you increase the temperature. That means we are looking at the shift of OH frequency as you increase the temperature, and we then measured it experimentally as well as we did with the molecular dynamic simulation. So, this becomes a combined molecular dynamic simulation. So, these are the spectra which are calculated, generalized spectra as you can see on the slide, but the same thing you can observe with laser Raman spectroscopy. So, we are also able to look at OH stretching frequency of the water and ice, and we found that the trends were extremely good. And that was sort of the beginning of combined molecular dynamics Raman spectroscopy technique for understanding advanced material interfaces. So, let me stop here. Now, not only you have seen that velocity autocorrelation is important with the simple harmonic oscillator, we also looked at how it connects with the vibrational frequency and the what we call selection rules with the different allowed states, quantum states. And now, based on that, you observe certain vibrational frequency in Raman spectroscopy. Now, you have good connection between experiment and the theory. Now, based on the experiment, we can improve our molecular dynamics model and look at that how we can improve the potential energy function, and then we get very good results in terms of what is the atomistic mechanism involved in the ice ice melting. So, this is where we came up with the model, is that what is the thermal induced fragmentation in ice lattice. So, before it becomes liquid, there is a thermal induced fragmentation in the lattice structure, and that was the study we conducted, and we published this paper in the famous reputed journal of chemical physics. So, this is how the real research connects with the molecular dynamics. So, thank you very much for this section, and we are going to continue with now different kinds of ensembles and how we calculate properties in them. Thank you.